You know those incredible, pure, beautifully structured crystals you see in a chemistry lab? Ever wondered how they're made? Well, it's not magic, not really. It's more of a methodical art form. And today, we're going to dive into a masterclass on the art of making chemical salts. I mean, just look at these. The color, the perfect angles. This is copper sulfate. There's a hidden order here, a precise recipe behind creating something this pure. So how does a chemist actually go from a couple of basic chemicals to these flawless crystals? That is exactly what we're going to break down. All right, here's our game plan. We'll start with the absolute basics. What is a chemical salt anyway? Then we'll hit the single most important decision a chemist has to make. From there, that choice will take us down a few different paths where we'll explore 3 key lab techniques: the excess, titration, and precipitation methods. Okay, first things first, when a chemist says the word salt, they are definitely not just thinking about what you put on your fries. They're talking about a massive family of chemical compounds with some very, very specific things in common. And here it is, the core idea. At its heart, a salt is an ionic compound. A really good way to think of it is as the child of an acid and a base. When those two react in what's called a neutralization reaction, they form a salt and usually some water. That's it. That fundamental concept is the key to pretty much everything that's going to follow. So now we're getting to the real heart of the process. Before a chemist even thinks about picking up a beaker or measuring anything out, they have to answer one single critical question. And this one decision, well, it determines the entire game plan. This is it. This is the big one. Will the salt you're trying to make dissolve in water, or won't it? Seems simple, right? But the answer sends you down one of 2 totally different paths in the lab. Think of it as the very first branch in our chemical decision tree. So how do you answer that question? You don't guess. You use a trusty solubility table, just like this one. Chemists pretty much have these rules memorized. For instance, you want to make any sodium salts or any nitrate? Look at the chart. All soluble, no exceptions. But what if you want to make, say, barium sulfate? You check the chart and boom, it's insoluble. This table right here, it's the map. Okay, so we've got our map. Let's head down the first path. For the next little bit, we're going to work on the assumption that the salt we want to make is soluble in water. All right, our first technique for making these soluble salts is the excess method. I like to call it the more than enough approach, and you'll see why in just a sec. It is absolutely brilliant in its simplicity. Let's go back to our copper sulfate example. You'd start with some sulfuric acid, and you just keep adding an insoluble base, like copper oxide, until no more of it reacts. You've literally added it in excess. Once the fizzing stops, you just filter out all the leftover black powder you added, and what you're left with is a pure solution of your salt, all ready for the final step, crystallization. And this just shows the process perfectly, doesn't it? You can see the reaction happening, then that all-important filtration step to get rid of the extra solid, and finally the evaporation and crystallization that gives you your beautiful final product. The real beauty of this method is that your starting base is a solid, which makes getting rid of the leftovers super, super easy. But what if your starting base is also soluble in water? Something like sodium hydroxide. You can't just add too much and then filter it out. It's all dissolved. So for those highly reactive metals like sodium and potassium, we need a whole different approach, one that's all about precision. And that brings us to the world of titration. This is the precision approach. It's one of the most classic and honestly elegant techniques in all of chemistry. So with this one, you can't be messy. You use a pipette to measure out an exact amount of your soluble base, your alkali. Then you add a few drops of an indicator, and you slowly, carefully add acid from a long graded tube called a burette. The very second the indicator changes color, you stop. You've just found the exact volume you need for a perfect neutralization. Then, and this is key, you do it all over again with the exact same amounts, but without the indicator, to get a perfectly pure salt solution. Yeah, this method requires some specialized gear. That long burette lets you add the acid literally drop by drop, giving you ultimate control. The pipette makes sure you start with a super precise volume of alkali. It is all about getting that ratio of acid to base perfectly, exactly right. And good chemists have little tricks to get this absolutely perfect. Putting a white tile under the flask makes that color change just pop. Swirling constantly makes sure everything is mixed. But the most important skill? Slowing right down to a drop-by-drop pace when you think you're getting close, so you don't fly right past that endpoint. It's a real craft. Okay, let's take a breath. We've just mastered the two main ways to make soluble salts. So now let's hit the rewind button. We're going all the way back to that first critical question, only this time our solubility map tells us the salt we want to make is insoluble. This leads us to our third and final technique, the precipitation method. And honestly, this one kind of feels like a magic trick. You're about to see a solid form right out of thin air, just by mixing two clear liquids. The strategy here is pure genius. You take two different soluble salts and you just mix their solutions together. The ions inside basically swap partners, and when the right two ions find each other, they lock together and form an insoluble solid that just appears. It precipitates out of the solution. After that, it's just a simple case of filtering, washing, and drying your brand new salt. And this diagram just shows it perfectly. You mix one solution that has barium ions floating around and another with sulfate ions. The second they meet in the beaker, bam, they combine to form solid barium sulfate, which is insoluble. The other ions, sodium and chloride in this case, they just stay dissolved in the water, kind of like spectators. It's such an elegant and instant way to create a solid. So, we've now covered all three methods, but for those first two, the soluble methods, there's still one final, really satisfying step to get from a simple salt solution to those amazing solid crystals we saw at the very beginning. This is the true art of crystallization. You gently heat your salt solution to let some of the water evaporate, making it more and more concentrated. You test it with a glass rod. You dip it in, pull it out, and if tiny crystals form on the tip as it cools, you've hit the crystallization point. Then the patient part. You just let it cool down nice and slow. As the temperature drops, the solution can't hold as much salt, so it comes out of the solution as pure, perfect crystals. And there you have it. Whether you're using the brute force access method, the precision of titration, or the instant magic of precipitation, the entire journey is just this beautiful exercise in logic. And it all flows from that one simple question: is it soluble? It really makes you think, though, doesn't it? This whole process, asking a key question, choosing a path, carefully executing a series of steps to get a pure result, that's not just for chemistry. Where else, in science, in technology, or maybe even in art, does that same exact pursuit of purity drive everything forward?